What'd you figure out? The one particular characteristic I called your attention to with the question was number of toes, right? Which way did you see toe evolution going in horses?
Like many toes to not many toes.
So starting with a bunch of toes and winding up with not a bunch of toes?
Yes.
Interesting. Yeah, I agree. And it turns out history does too. So let's play my favorite game, which is, what was the advantage there? That's my favorite evolution game, is to look at something that obviously had to be an advantage or it wouldn't be here. Why would that be an advantage? What good is it, is really kind of the name of the game. What good was that? What good was that for horses? Why did it give horses an advantage over their neighbors and let them have more babies than the horses who had more toes? Remember that it is environment that drives natural selection, and this is a case of that. Colby, what do you think?
Because they rougher terrain.
Which? More toes or less toes? More toes, you think, would handle rougher terrain?
Yeah.
I like that. But that's not the direction horse evolution went. Maybe they started on rougher terrain, which is why they needed the more toes. What happened, do you think, to drive them towards less toes?
Kind of like leisure, because more toes are used for like agility and like skill and like weaving for like maybe like predators.
Okay.
But as we breeded them and domesticated them for like our commercial needs, not really like leisure, but like for riding horses through terrain, it would be better to have those hooves for like always on the ground contact and not really like darting.
That makes some sense, except that you're coming into like human selective breeding of horses, when in fact the modern horse existed by 2 million years ago in a pretty similar form to what it is now. We've definitely messed with it some, not a lot. And so this wasn't humans that did this. It wasn't that they got lazy. Something must have driven them from more to less toes. What do you think, Will? So Colby nailed it with the many toes. That's great for like picking your way over like rocky stuff. What if a subpopulation of horse ancestors suddenly winds up like on flat hard pan, straight up like pancake ground, real hard ground that goes flat for miles and hundreds and hundreds of miles? Suddenly it's not quite as much of an advantage to have more toes in contact with the ground. If there's something real fast chasing after you that wants to eat you, maybe suddenly the less you have in contact with the ground. You ever ride like a road bike versus a mountain bike? What's the difference in tires? What's a road bike's tires? Yeah, like pencil thin tires on a road bike, trusting basically that you're going to be on real flat ground. And so the less wheel, the less tire you have in contact with the ground, faster you're going to be. And that's horses. That's horses evolving from 4 toes to basically 1 toe with a giant fingernail underneath it, right? To keep the ground from hurting that bone. Yeah, so that's one part of that story of horse evolution. I'm interested to see what you did with the rest of it. Okay, so from fossil evidence, grab your notes. Because fossil evidence is great. We like fossil evidence, but we have so much more now. With what we know about evolution, we can use lots of different lines of evidence to figure out things about what's related to what and how evolution has happened over the billions of years life's been here. Today we're going to go through 3 different kinds of structures in living things, not extinct ones, although you can use it with extinct ones, but structures you can observe in living species today that can give you information about how living things evolve. And then we'll get to the molecular level and you'll get to figure some DNA stuff out. I know you missed DNA, so we're going back to it. What you're looking at here is the skeletal structure of 3 different mammals. This is a bat wing. This is a mouse forelimb or front paw, I guess you'd call it, and this is a human arm. Notice there's similarities and there's differences, right? Kind of the same basic parts list, same basic number of bones and placement of bones, but those things in these adult forms of these mammals have adapted to quite different jobs. This thing flies. Think about the adult, like if you're not looking at the skeleton, if you're looking at the whole bat, think about that bat wing versus that mouse front paw versus that human arm, how different they are in their adult forms. But here's the thing about these three. If you look at an embryo at a certain fairly late stage, in fact, of a bat, a mouse, and a human, you would have a very hard time telling these three structures apart. The exact same blocks of tissue, and up to a very late point in that embryonic development, they look exactly the same. It's in as they get to maturity that those things become very different. Structures like that give us big clues to evolutionary history. They're called homologous structures. Basically, they're different in the mature form of the organism, but develop very similarly in the embryo. Basically, what we know is that embryonic structures stay physically similar much longer than mature structures do. In other words, as big changes happen in adult structures, those changes don't look as big when you're in the embryo. And so by looking at embryos and the similar ways things develop in embryos, you can start to get clues about who's more related to whom. And so basically looking at these three in the embryo, noticing they're almost identical in the embryonic phases of a bat, mouse, and human, what you're learning is, hey, there's a common ancestor there. These are all mammals. And that's why there's such similarity at embryonic level, even though those things have been adapted for three really different jobs, right? One is for flight, one is for whatever mice do, holding stuff and eating it, digging a little bit. And one is for like typing, like piano, manipulating tools, wow. Homologous structures. Similar because of common ancestors, because they're related, and much more similar in early development than in adult forms. And you can see homology, as we call it, all over the place. You know, everything ultimately is related. So you start to look at the different mammals and you see homology, but you can also see it in different groups, like amphibians, right? Same deal, all working from the same basic parts list. But now, let's look at a different kind of similar structure. I'm about to show you a bird, a fish, and a mammal. Bird, fish, mammal. Pretty different groups of vertebrates. Like as different as you can get and still be a vertebrate, right? And yet, if you met them in a dark alley, you might not be able to tell them apart. Bird, fish, mammal. Okay, maybe you could tell them apart in a dark alley, underwater. But man, there's a lot of similarities, aren't there? What do you see? what do you see that these three distantly related vertebrates have that are similar? Yeah.
Fins.
Fins, what do you mean?
Like their arms.
Arms, in a sense, at least in the mammal sense, for sure. That's where an arm would be in a non-aquatic mammal. And yet here it's like a wedge-shaped flat thing, right? Well, here it's not an arm, it's a wing, because that's a bird. But look how similar. Almost identical. Just one's covered in feathers, one's not. And then here, there's not even a bone there. That's all cartilage. And yet, very similar. What else is similar about them? Describe that shape. Ooh, submarine, I like that. Or you could say like torpedo shape, like kind of tapered in the front and then gets a little wider in the back and then tapered back again. Good. Anything else? Couple things that, maybe two of them share, like the dorsal fin here. Almost identical placement and shape. Propulsive tail, a tail that helps you swim. This one's horizontal, this one's vertical. This one's like a combination of foot and tail, but still, right? So are these three animals similar because these are homologous structures? Are they similar because they're so closely related? No, I mean, they're working with different parts in a lot of these cases. Why are they so similar then?
Sorry for the interruption. Emma Ward, would you come to you and stop us, please?
You said environment. What environment are we talking about? They all live in the water. They're all vertebrates that live in the water. And it turns out there's a limited number of ways to be awesome as a vertebrate in the ocean. And this is one of the best ones. Analogous structures are what we call these. And they're similar not because of common ancestry, but because of common environments. And what you get, especially with demanding environments, is, you can get critters that are from very far apart places, halfway across the globe, but still really similar environments, and you can see things that look pretty darn similar. Not because they came from a common ancestor. But because their environments were so similar. And the niche they fit into was so similar that they separately evolved really similar adaptations. There's not that many ways to be a predator in the water if you're a vertebrate. Being able to swim really fast is probably the best one. Or one of the best. I guess camouflage in an octopus is another example. But boy, an awful lot of them have developed the torpedo-shaped body, the fins in very similar places, because that's a really good way to be fast and maneuverable in the water. That process of different species starting out morphologically, physically different, and then evolving to become more similar because they have similar environments, that's actually called convergent evolution, as in to converge, to come together, right? So homologous, similar because of common ancestry, and even more similar when you look at embryos. Analogous, similar not because of common ancestry, but because of similar environments. Then we have our third kind of structure. This one, I bet you can come up with a couple on your own. Think of something on you, on a human, that you'd have a real hard time thinking of a good use for it. Something on you really isn't of any use at all.
Pinky toe.
Pinky toe. Yeah, maybe a little bit of balance there. But boy, that thing's kind of shriveled up and weird looking, right? Pretty useless. Yeah, I like it. What else you got? Tailbone. We call it a tailbone. That's interesting. Yeah, it comes down a little farther than you'd expect to be really useful. Will? Eyebrows.
I don't know about that. Those might be useful. They keep sweat out of your eyes, maybe. Maybe they even darken the sun like the dark marks underneath you. Yeah, maybe. Yeah, that's a good example. I like it.
What else?
Make sure your appendix is.
That's a good one. The appendix is a really good example of one of these kinds of structures. Do you know what your appendix is? It's like about the size of half of your pinky maybe, and it sticks out the corner of your large intestine. It's just a tiny little pouch. Really doesn't do you any good. And if the wrong stuff that you eat gets stuck in it, it can get inflamed and explode and like kill you. Thanks, evolution. Anything else you can think of? Tonsils. I like that. That's one that we're less sure of than we used to be. It's definitely something if you get the wrong kind of infections repeatedly, they'll take them out and it'll help. But there's also some evidence that they do some good when they're in. So it's a tough call sometimes. All of these are excellent examples of what we call vestigial structures. And while they might be useless to you, they sure are great for studying evolution. We wind up getting to dissect. Those of you that get the rat, we dissect rats in here. And what you'll notice as soon as you get into the abdominal cavity of that rat is that, man, their large intestine is different from ours. It's got kind of a part of it that looks like yours, but then there's this big old blind pouch coming off, like right about where the appendix should be, but way bigger. And by blind, I mean it's like a dead end pouch. Kind of like your appendix, but way bigger. And that's because rats basically eat everything. They eat garbage, right? They eat like dead animals, bones and teeth and all. They eat gross stuff that has things that are basically undigestible. They need a place for the really undigestible stuff to go and sit and soften for like weeks at a time so that it doesn't hurt them coming out. You get it? So the pouch is called a cecum, C-A-E-C-U-M, I think. And lots of mammals have it if they eat stuff that, would do damage otherwise if it didn't soften up. Whereas humans, at a certain point in our evolution, stopped eating stuff like that. And so the cecum went away, except not completely, right? There's this little part of it that stays, and that's the appendix. But it's a huge clue to your ancestry, right? To what your ancestors had because they ate garbage. So these are inherited structures that have basically lost most, if not all, of their function. And they're clues. Man, they're great clues. Another example of a vestigial structure in humans, how about body hair? How weird is that? Not just body hair, but I'll take it a step further and go goosebumps, which is these muscles at the base of each body hair you've got, called the erector pili muscles, that when you get cold or scared, cold or scared, whoop, those muscles flex and all your little hairs stand up. And you get little, called goosebumps because it looks like a plucked bird, right? What? Why? What use could that possibly be? Well, not much to you. It's a clue, though. What's it a clue of, Mana? You can see that in modern cats. They do that, right? They get real scared and go fight or flight, and their hair goes out. Suddenly, that's a bigger cat. Yeah, That's what that's for, in critters that have lots of hair, unlike you, weird bald monkey. Right? And what about the cold thing? Well, if you think of someone who's got lots of body hair as someone who's basically wearing their own little sweater, flexing all those little muscles, standing the hairs straight up, a lot of air spaces in between those hairs, you're basically giving yourself a thicker sweater. If you've got enough hair, which we don't, right? But it's a clue to your ancestors. That's what vestigial structures do for us. Here's a non-human case. It's pretty cool. Anybody ever been to the Smithsonian Museum of Natural History in DC? I was so excited. This was only like 6 or 7 years ago that I went for the first time. And this example that I teach in class, like actual fossilized skeletons of these critters hanging above you in this one hall in the Smithsonian. Whale ancestors. Kind of like the horse, we've got pretty good sequential fossils of whale ancestors. And one of the things you can see in those whale ancestors is legs going away. First of all, the legs becoming adapted to swimming, right, with wide toe bones and stuff. But then basically the legs, and we're missing some intermediates here, but the legs go away, but you know what doesn't? The pelvic bones, the anchors for the legs, still there. Still there. Ridiculous, just floating there, not really attached to anything. It's a clue. Useless hip bone? Oh, his ancestors walked. So super useful, vestigial structures, to give clues to evolutionary paths. 3 lines of evidence: homologous, analogous, vestigial structures. They tell us different things. They're all useful, and you can see them in living, non-extinct species. Questions?
Why is this like bone structure?
Oh, like this? So that's an adaptation for basically massive filter feeding. You know, baleen whales, they have those bristles that filter out plankton. Well, if you're gulping in enough water and forcing it out through those bristles, that's an enormous amount of stress on your skull bones. And so this huge bone is necessary so that basically it doesn't crack his own skull with all that water force. Yeah, okay, so moving on from that to the really kind of nitty-gritty genetic stuff. Ooh, write that down and then we'll puzzle this graph out. Back to descent with modification. The longer it's been since you had a common ancestor, the more different your DNA ought to be, right? The longer it's been since you had that common ancestor, if we measure your DNA, it ought to be more different. Except that measuring DNA is a super duper pain in the butt. You have so much of it. You know what's easier? Finding a protein coded for by DNA that everybody shares and looking at differences in the amino acids of that protein, because differences in amino acids equals differences in DNA. And now we've only got to deal with one gene's worth. So one of the proteins we use as what we call a molecular clock, as in you can measure differences in it between 2 different species, and the more there are, the longer it's been since they had a common ancestor, is called cytochrome C. You actually know cytochrome C, even though you don't know you know it. I'm just gonna bring back some, let me do it here. I'm gonna bring back some trauma real quick. Do you remember? No, not yet? Okay, how about this? Oh, man.
That's not the
Right? Cytochrome C. It's one of the little things that dinks the electron along the electron transport chain, which means that every organism on the planet that does the electron transport chain has it, which means they all have the gene for it. And it has to work, so it doesn't change very fast. So basically what this diagram I just showed you is counting the number of amino acids, says substitutions means differences. How many amino acids are different between birds and reptiles in their cytochrome C? That's it. That's all this is. And the more differences there are, the longer it's been since they held their conference. Make sense? Good. That's your job for today. You're gonna make yourself a little molecular clock. Now this packet comes with a little bit of sticker shock. See what I mean in a minute. I want you to turn to the very last page of this packet, the very back of this packet. Go ahead and do your freaking out. I know, it looks scary, right? No. Notice we've got a key in the lower right. A through Y, each of those letters stands for a different amino acid. There's only 20 amino acids. But here's the thing, you don't have to know that key at all. You're not gonna have to use that key at all. It doesn't matter. What matters is finding differences in the cytochrome C protein, which, by the way, take a look, it's 2 lines long. Top half of this page, bottom half of this page, same critters. It's the first half and second half of that same critter's cytochrome C protein. So don't make the mistake of just looking at the first line. You got to look at the first line plus the second line. And all you are doing from the front, take a look at the front, and it says number of amino acid differences, below number 2 here. Number of amino acid differences between human and. So you're always going to be looking at the human line, which is the underlined one, 2 lines long on the back. Then you just go through each letter and compare it to, first of all, the rhesus monkey. And every place along these 2 halves that you find a different letter between the human and the rhesus monkey, circle it on the rhesus monkey. By the time you're done, you'll have a number. That number is going to go next to the rhesus monkey. Then you're going to do the same thing with kangaroos, snapping turtle, bullfrog, and tuna. Make sense so far? You done with that? You get to turn to the second page. Those numbers you just found, you're going to write them in the hexagons on the tree of life on that second page. Okay? And that'll get you going, and then you got questions to answer, and that should go fine. Okay? Any questions?